urban areas produce roughly 70% of global CO2 emissions. To meet the reduction targets set by the Paris Agreement, these cities have to accurately account for their greenhouse gas outputs. Currently, municipalities rely heavily on bottom-up tracking methods. They compile statistical data on fuel consumption, traffic, and industrial activity to estimate their carbon footprint. Because these statistics often lack precise boundaries and rely on broad assumptions, the self-reported figures carry enormous uncertainty. Comparisons against independent data products have revealed emission reporting errors ranging as high as 145%. To correct this, scientists are deploying top-down verification. Rather than counting activity on the ground, this method measures the actual physical gradients of atmospheric carbon accumulating over a city. By gathering concentration data from physical sensors, researchers can use atmospheric transport models to run mathematical inversions, calculating backward from the measured air to find the true emission source. Without integrating complex fluid dynamic modeling, local governments are left managing their climate neutrality goals using statistical estimates rather than physical evidence. To test a high-resolution transport model capable of this verification, researchers selected the Swiss city of Zurich. Zurich sits within a highly complex topographical layout. The dense urban core extends primarily along the floor of the Limmat Valley. To the west, the city is bounded by the steep Albis mountain ridge, peaking at 870 meters above sea level. The eastern edge is walled in by a series of densely wooded hills, culminating in the Adlersberg Ridge at 701 meters. This Shark Valley basin heavily distorts synoptic weather patterns. The changing, opposing elevations create highly localized atmospheric flows that shift rapidly based on temperature and air pressure. At ground level, the problem intensifies. The rigid geometry of the urban architecture fragments the wind, forcing carbon plumes to weave through narrow streets and deflect wildly off the varying building heights. Running continuous computational fluid dynamics to track these micro-distortions in real time across an entire city requires an impossible amount of processing power. To bypass this limitation, researchers implemented the GRAMM/GRAL framework. This two-part modeling system mathematically isolates the macro weather patterns from the microscale street physics. The first layer of the framework relies on the Graz mesoscale model, or GRAMM. GRAMM establishes a 30 by 30 kilometer boundary centered directly over Zurich, divided into a grid of 100-meter blocks. Within this domain, the model calculates the non-hydrostatic atmospheric flow forced by the surrounding mountains and valleys. The flow parameters are adjusted to account for surface variables, mapping the physical roughness, heat capacity, and albedo of the specific terrain beneath it. This map shows output shifting under different stability classes. In the left panel, under stable conditions, cold air drainage flows cascade down the Adlersberg Ridge into the center. The right panel illustrates an unstable environment, tracking thermally induced lake breezes moving inland. Calculating these large-scale topographical wind distortions provides the rigid mathematical boundaries required to simulate flow at the street level. The mesoscale calculations are then handed down as lateral inflow boundary conditions for the second layer of the framework. This is the Graz-Lagrangian model, or GRAL. It operates inside a tighter, nested 13 by 13 kilometer domain right over the city center. Here, GRAL calculates the Reynolds average Navier-Stokes equations, projecting how incoming wind navigates the physical geometry of individual buildings. This microscale fluid dynamics calculation is executed at a strict 10-meter resolution, capturing the aerodynamic drag of the urban architecture. Once the wind flow is mapped, GRAL activates a Lagrangian particle dispersion model, introducing virtual particles into the grid to represent volumes of carbon dioxide. These virtual particles are linked directly to an inventory of 24 highly specific emission source categories distributed across the city. The framework isolates 17 anthropogenic sources, including road traffic, heating, and large point sources, alongside 5 distinct biospheric sources. Accurately mapping those biospheric fluxes, particularly the carbon uptake from the heavily wooded Adlersberg Ridge, is a mathematical requirement to isolate the human-made carbon signal. Operating at a 10-near resolution, this computational fluid dynamics model effectively translates abstract emission statistics into physical concentration plumes interacting with the city landscape. Calculating continuous 10-meter resolution Navier-Stokes equations for 8,760 hours in a year would stall any standard computing cluster. To circumvent this hardware limit, the research team engineered a database catalog optimization, pre-calculating steady-state dispersion fields for 1,120 distinct combinations of wind direction, speed, and atmospheric stability. They built a mathematical matching algorithm to pull from this database on demand. The algorithm uses an entry term, eta-h, to query the database, snapping to the single matrix tile that best matches live weather. The model then applies a temporal scaling factor, tau-hh, scaling the annual average emissions of a specific source to match the exact hour, accounting for daily traffic peaks or winter heating. The final concentration is produced by adding the city's specific catalog state to the baseline carbon levels flowing in from outside the grid. By pre-computing the physics and separating the temporal variables, a computationally impossible fluid dynamic simulation is reduced to a rapid, highly accurate database query. To confirm the accuracy of the catalog algorithm, the resulting concentration models must be tested against live, physical data. This map shows the Zikos-M sensor network, overlaying 77 observation nodes across the computation zone. 60 low-cost sensors mounted close to the ground measure localized street emissions. 22 highly calibrated mid-cost sensors, positioned above rooflines, capture the broader concentration gradient across the city. The computationally generated concentration plumes are matched against the precise physical readings pulled from these nodes to validate the model's accuracy. Topography-driven winds calculate the mesoscale boundaries. A Lagrangian dispersion model maps the microscale carbon flow, and the resulting pre-computed catalog is verified against a dense grid of live sensors. Through atmospheric transport modeling and physical sensor networks, cities can transition away from statistical guesswork and measure their climate neutrality progress with physical certainty.